Now we are doing particle physics second part. And the first thing that we need to discuss is standard quark model. It's a model in which we discuss the fundamental particles which are quarks. There are two types of quarks, one with charge plus 2 by 3e. The other type, second type, is with charge minus 1 by 3e. And all the quarks have a property called baryon number. The names of the quarks are, first of all, first pair is up and down. Symbol for up is U and symbol for down is T. And their baryon number is plus 1 by 3. So this is the first pair. The second pair of quarks is charge, symbol C, and strange symbol S. And their baryon number for both of them is plus 1 by 3. The third type of quarks is top for T and bottom for D. And their baryon number is obviously plus 1 by 3. So first pair, second pair, and third pair. There are the three pairs of quarks. When these quarks combine, they make the baryons. Now E stands for elementary charge, and its value is obviously 1.6 into 10 power minus 19. So E is the elementary charge with this value. Now if you are asked to list antiquarks with their symbol, with their charge, and with their baryon number, then the antiquarks are number one. We have anti up, we have anti down, we have anti charm, we have anti strange, we have anti top, and in the end we have anti bottom. Anti up, this is the symbol. Anti down, this is the symbol. Anti charm, this is the symbol. Anti string, this is the symbol. Anti top, this is the symbol. And anti bottom, this is the symbol. Charges are plus 1, sorry. Anti up would be, up was plus 2 by 3, it would be minus 2 by 3. This was minus 1 by 3. Then here you see this down has a charge of minus 1 by 3. So here it will have charge of plus 1 by 3 because it is the anti-quark. Anti-charm will have a charge of minus 2 by 3e, as a charm has a charge of obviously 2 by 3. Now Now, anti-strange has a charge of plus 1 by 3e, anti-top has a charge of minus 2 by 3e, and anti-bottom has a charge of obviously plus 1 by 3e, and all the quarks, anti-quarks have a baryon number of minus 1 by 3. All of them have a baryon number of minus 1 by 3. Now, composition of a proton and a neutron. A proton and a neutron both are baryons, and they're the types of hadrons. Now, their composition. Number one. A proton is made of three quarks. A proton is made of three quarks, which are up, and down. A neutron is also made of three quarks, which are down, and up. So a proton is made of three quarks, and a neutron is also made of three quarks. For a proton, we have up, and down, and for a neutron, we have down, and up. These are the composition of a proton and a neutron. So this is the composition you need to remember. A proton could be represented as it has an upward, another upward, and a downward. And a neutron it has two downwards and one upward. So this is composition of a proton and a neutron. Now the next thing is, if the examiner asks you a question, which of the following are conserved, in a nuclear reaction? Which of the following are conserved in a nuclear reaction? The first thing is number one, mass. The answer is it is not conserved. Reason, as mass and energy are interconverted. Energy is also not conserved for the same reason. Not conserved. So in a nuclear reaction, either mass or energy, both of them are not conserved. Then we define a new quantity that is called mass energy. Mass energy is a new quantity that is conserved in a nuclear reaction. Mass energy is conserved in a nuclear reaction. The fourth quantity that we need to understand is after mass energy, it is momentum. Total momentum, total momentum is always conserved in a nuclear reaction. So the fourth property that is conserved is the momentum. Nuclear reactions are treated to be isolated. So this was number 4. Number 5 should comment on the protons. Protons are not conserved as protons and neutrons are interconverted. The sixth property whose conservation is to be discussed is the neutrons. In a nuclear reaction, neutrons are not conserved for the same reason. Neutrons are also not conserved, and the reason is the as the protons and neutrons are interconverted. Then the seventh property that we will discuss is nucleons. Nucleons are the sum of protons and neutrons. And since protons and neutrons are interconverted, yet their sum remains constant. Nucleons are conserved, which means that the sum of protons and neutrons is always conserved. The eighth property that we have to discuss is leptons or lepton are conserved. Now, these are the properties which must be conserved in a nuclear reaction. There are two nuclear reactions which are important and we need to understand. One of them is positive beta decay. One of them is positive beta decay. Basically, I will write positive with P for the reason the reaction also starts with P. Positive beta decay. In this reaction, in a positive beta decay, a proton converts into a neutron. These are the numbers. Like proton has number 1, which means it has a charge of 1 and it has a mass of 1 as well. This is a standard notation. Below the symbol we write the charge and above the symbol we write the mass number. Then we have neutron and the charge is not balanced. On the left hand side we have a proton. When it is proton to neutron, it is the positive beta that is eliminated, that is emitted. And positive beta is, as you see, it is anti-lepton, it is anti-electron. The charge is balanced, but the electron numbers are not balanced. A lepton, electron, neutrino, or some other electron is also ejected to give a balance to the reaction. Now, this is a lepton. So, an anti-lepton and a lepton both are ejected in a positive beta decay. You must remember in this way. if you want to memorize positive beta decays, you memorize that positive starts with P and proton will also start with P. Then we have negative beta decay. Negative starts with N, and it's a coincidence that the reaction will also start with N. So to memorize it, you should remember the positive and negative. Positive with P, positive starts with P, negative starts with N. So negative beta decay. In a negative beta decay, neutron is converted to a proton. A neutron is converted to a proton, and along with that, a negative beta particle to balance the reaction, and an anti-electron neutrino countered electron are also emitted. So this reaction is called negative beta decay. So this is positive beta decay, and this is negative beta decay. So we are done with nuclear and particle physics. In the next lecture, we'll cover the new topic. Take care, students. Allah Hafiz.